Questions 1, question 1 and 2 on Kirchhoff's laws are adequately covered in the 2 videos that are posted. But I'll write out the 3 equations that I would use to solve this circuit, and you might try doing that if you're here, and then see what I do and see if it agrees with what you did. Okay, there's the loop equation on the left, 12 volts, a voltage drop in the direction of the current, so minus the resistance times the current, minus the resistance times the current closes the loop. Similarly for this loop, and then I wrote the junction equation there. So those 3 equations would allow you to solve this problem. The algebra would not be quick, but just to give you an idea, I would take I1 plus I2 and substitute it in here for I3, use the distributive law, and come up with 2 equations with 2 unknowns, just I1 and I2, and then I would use methods of algebra to solve that. You can go to the longer video if you want more help with this. I'm going to now move on to the other RC circuit problems. Okay, do as much as you're able to do before you watch what I do, but I'll walk you through this if you need help. Okay, we always start with the capacitor, and since it's empty when the switch closes, it can't instantaneously charge. So that means the voltage across the capacitor and the charge on the capacitor have to start at 0, and they will rise. They will do the charging exponential behavior. The current through a resistor can instantaneously rise. It's able to do it. And by Kirchhoff's loop rule, since the voltage across the capacitor is 0, the voltage across the only resistor that's in this circuit, right, we have it closed here, R2 is out of the circuit, so we can take I2 and R2, I2, and V2 are going to be 0 throughout this problem because it's not really connected. And so the voltage across R1 has to be the battery voltage because the sum of the voltages have to be 0. So I have 24 volts, and the current then is simply going to be the voltage divided by the resistance. That would be 24 volts divided by 250 ohms, which gives me 96 milliamps. So those are the starting values. And the graphs, these 2 are meaningless, so the capacitor and the capacitor's charge and voltage is going to do this, and the voltage across the resistor and the current through the resistor are going to do that. And the next question will have you graphing them. I won't do that now, but just to show you, and those 2 equations are the charging equation would be, if we were looking at the voltage across the capacitor, it would be Vmax 1 minus e to the minus t over the time constant RC. And the voltage across the resistor, which is decaying, is just the maximum voltage, simply e to the minus t over the time constant RC. And you do need to use those equations to calculate these values. Let's come back to those. Let's go to the ending values. So from this, we can see that, of course, as we said, the second resistor isn't really in the circuit. The voltage across the first resistor starts high and goes to 0, and so does the current. And as that, the voltage across the capacitor will charge to a limiting value of 24 volts and to a maximum charge, Qmax, will be C times Vmax. And that is 24 times 40, which is 960 micro, right? Microcoulombs. So it would be 0.960 millicoulombs, moving the decimal point 3 places. Okay, let's see how we get these middle values using these equations here. Okay, so what we know is these values are not relevant. They're at 0 because it's not really connected. And the voltage across the capacitor is going to discharge. And so I'm going to use this equation. I calculated the time constant, which is 250 times 40 equals 10,000 microseconds, or 10 milliseconds. That's our time constant, 10 milliseconds. And we want to know what's the value at 6 milliseconds. So substituting those numbers in the equation. And since I know when it's e to the minus 1, this is what you want to try to remember. E to the minus 1 is 63% charged, so this is less than one time constant. So I guess that it would be about 50% charged, and when I do the calculation, I get a value of 13.17 volts, or 13.2 volts to 3 significant figures. Now we can actually find the voltage across the capacitor by subtracting that from 24, or we can do the calculation that the voltage across the capacitor is going to be Vmax, 24 volts, 1 minus e to the minus t over RC. And if we do that, we should get the 13.17 subtracted from 24 as the value for that, equals 10.83 volts. I'm not going to write those in. And now we can use the voltages across the resistor to find the current through the resistor and the charge on the capacitor. And those are the two equations that you would use to get the charge on the capacitor. So the voltage for the capacitor, that's the voltage for the resistor, divided by the resistance of that resistor, right, R1. And that's the voltage across the capacitor times the 40 microfarads. I'm not going to do those numbers. You can get those. And that completes all those values. Okay, the next question, 4, is very similar to this, only it's about graphing. So there's some questions here. I think you can answer them. There's some examples of the graphs, but we want to be sure we can graph them. So I'm going to go down here and look at the values we're given, right? We have this circuit here, and we're going to try and generate those graphs ourselves from the values that we're given. So let's take a look at this, and let's graph one at a time. We'll start with graphing the voltage across the capacitor. So the first thing we want to do is get the starting and ending values. Actually, they're not the ending values, they're the values that are approached as time goes to infinity, right? Because it never actually reaches those values. So calculate these 9 quantities and then come back. So we know the capacitor charge starts at 0, can't change instantaneously, so it's going to start at 0 and go up. The voltage then, because it's no charge, means no voltage. That means all the voltage will be across the resistor. And since only R1 matters, right, R2 is not really connected to the circuit in this case, the current will be 33.3 repeating milliamps. And the capacitor will charge to 10 volts as the resistor decays from 10 volts to 0. And the final maximum charge on the capacitor will be the voltage times the capacitance, or 360 microcoulombs, or 0.36 coulombs, and the time constant is RC, and that's 10.8 milliseconds. So these are the values that we need to do the graphs. So I'm going to change the screen, but save those numbers. So let me walk you through the first graph. First we draw the axes. We put in the maximum value. I'm doing VC. So I label this axis VC. Notice all the steps. You're going to have to do this. I put the units in parentheses. It's volts. I put in the maximum value. Remember, it'll never reach that value. I draw a dotted line. It's going to approach that value. And then I'm going to show 3 time constants. We could show more. The graphs do show more. So make those evenly spaced. And so this is the time axis. So label it time. The units we're using are milliseconds. Make sure you put that label down. And then this is going to be 10.8, 21.6, and 32.4. I did that in my head. It should be right. So those are the 3 time constants. And what I know for the voltage and the charge, after 1 time constant, it's, right, e to the minus 1 minus e to the minus 1 equals 0.632. So about 2/3. So I just, with my eye, I go up about 2/3 of the way and put a point. Then the remaining distance between that point and the top, for the next time constant, I go another 2/3 of the way and I put a point. And you see that small remaining distance, I go 2/3. And when you do the problem, you'll find out that the 2 time constants is about 86% charged, and the 3 time constants is about 95% charged. So with these 4 points, I can sketch out the graph. And without doing any calculations, now notice I didn't touch the line because it doesn't touch the line. Even after 5 time constants, it's 99%, but not touching. So that's what the graph looks like. The axes are all labeled. And now I'm going to write the equation. So this is the equation that I just graphed, is the voltage across the capacitor is the maximum voltage, 10.0 volts, 1 minus e to the minus t over the time constant, 10.8. Notice I'm putting the numbers in, and the units milliseconds. That's the equation. Now you want to do that for all 4 graphs. The charge on the capacitor is going to follow the same pattern. The shape of the graph is going to be the same, only you'll have, what was it, 0.36 millicoulombs for this maximum value. Your labels will change. This will be QC, this will be millicoulombs, but the time axis stays the same, and the equation will be QC and Qmax, which is the 0.36 millicoulombs. Not writing very well. So just by changing those, I have the other charging. Now the current and the voltage are going to decay. Let's do that together. Okay, I set up the axes, and notice that I have the maximum value that it's going to approach. I have the label for the axes, the units, the time axis is labeled, the 3 time constants are shown, and now I want to put in the 4 points. It's going to start at the maximum value after 1 time constant. It's going to come down 0.63, or about 2/3. So I'm not going to count. I'm just going to look at it by eye, and then another 2/3 of that remaining distance, and then the final 2/3 where I'm down to 95%. And now I can use those points to sketch out, those 4 points to sketch out the graph. And making sure that it approaches but doesn't touch the x-axis. The final thing is the equation of the graph. And there's the equation. Notice I put in the numbers with the units, and the voltage is going to be almost identical, right? And the graph, the equation, the only number you need to change is the maximum value, and for the graph you just need to change this number, this label, and this unit, and the graph will have the same shape, decaying exponential. And that completes question 4. Okay, question 5. Read over this. So what we're going to do is we're going to close the switch horizontally and let it remain there for a while. That means the capacitor will be charged, just like we did in the last 2 questions. Then from this position we're going to close it down. So when we close it down, we disconnect the battery from the circuit, we connect R2 to the circuit, and now we have a circuit of a capacitor which is charged and 2 resistors. And so what you want to do is you want to calculate the starting values for that circuit when the switch goes from horizontal to down, and the ending values that they approach as t goes to infinity. Then after we do that, we'll come back and calculate the middle values. So get the starting and ending values first, and then come back. Okay, so we start with the capacitor, since it can't change instantaneously. And so the capacitor was 10 volts, so when it comes down it has to start at 10 volts, and it was fully charged at 0.240 millicoulombs, and that's what it'll start at, and it'll decay. But the capacitor will decay through the resistors. So notice you have a simple series circuit where the capacitor is acting like a battery and current is going through the 2 resistors. Since they're in series, the current in both resistors has to be the same, but to find it we have to use the total resistance. So the total voltage, 10, divided by the total resistance, 710, gives us in milliamps 1408 milliamps. So we have current through the 2 resistors at starting at 14.1 milliamps. Whoops, I put those labels should be reversed. The 14.1 goes down here, and the voltages go up there. So once we have the current, we can find the voltage, because those 2 voltages are going to add to 10 because of Kirchhoff's loop rule, right? The voltage rise has to equal the voltage drop. So we get the voltage across R1 simply by multiplying the current through R1 times the resistance R1 300 ohms, and we get 4.23 volts. And for the other doing the same thing, only 410 ohms, we get 5.77 volts, and those do add up to 10 volts. And I don't put negative signs because the question just asks for the magnitude. And the final values, they're all decaying exponentials. So all these graphs are going to be decaying from a large value to 0 according to the time constant. And we'll graph that in the next question. But let's proceed to the middle question. And to calculate these values, you need the time constant. And remember that to get the time constant for this circuit, you have to use the total resistance. So see if you can do that. Okay, I'm just going to do one of them because they're all identical. They're all decaying exponentials. So let's find VR2, which was 5.77, e to the minus t over the time constant. So the time constant is the total R times C. So that's our time constant in milliseconds. And we want to know what will the voltage be at 8.52. So we have the time over the time constant. It's negative. And we multiply that factor times the 5.77 volts, and I get 3.50 volts. So just follow the same procedure for all of them. Start with the correct maximum value, and this factor is going to be the same because they're all asked to find them at this time. Okay, done. Okay, last question, graphing the decaying values. There'll actually be 6 graphs here. We won't do all 6, but they're all decaying exponentials. So we're only using these equations here. So anyway, we have a different set of values, so we know the ending values are all 0. Find the starting values, and then we'll graph a couple of these together. They're very similar to the decaying exponential graphs that we did in question 4, but I'll do 1 or 2 of them here. So calculate those values and come back. Okay, if there are no errors in my calculations, the values all end at 0. These are the starting values, right? It starts at 16 volts. I calculated the maximum Q that it starts at. Then I used the 2 resistors. You can see my calculations. I got a time constant of 23.7. That's what we'll use for the graphing. And I got a total current of 16 divided by the total resistance. So that means that's the current going through both resistors. And that gives us the voltage across the 2 resistors summing to 16. So that all looks good. And so every one of these 6 quantities is going to decay exponentially from its maximum value according to e to the minus t over the time constant. And let me pause and do at least one of those. So I labeled both axes, and I'm plotting voltage across R2, which will start at this and decay. And then I'll use the rule of after one time constant, it's 63% decayed or 37% remaining, roughly 2/3. So I'm going to put a point, the high point to start, about 2/3 of the way down, another 2/3 of the way down, 86%, and then 95% decayed. And I can graph write the equation. So this is IR2, and it's going to be the maximum value, 9.11 volts, times e to the minus t over the time constant, 23.7 milliseconds. So that's the equation that I just graphed. And all of the others are going to look like that, only the labels will be different, the maximum values will be different, but the shape in every case is going to be identical. Okay, I think we're done. And finally, here's the table of contents, looking backwards.